literally running out of time, but that's fine.
That's okay. We'll be asleep by then.
Anyway. Okay, so you end up with this. So T of A, B, C, D plus T of E, F, G, H. And what we're trying to do is get them split into two separate parts. So what am I going to do when I get to this mess? Let's pretend for a minute you don't know what to do. I think Deshaun knows what to do, but let's just say we don't know what to do. What we can do if we don't know what to do is go to the other side of the formula that we're trying to get to. Okay, so I need to keep reminding you. Basically, the formula is, we started from here, right? We're trying to get to this side. Okay, so we could come and work on this side instead. So that's what I'm going to suggest we do. So let's take T of A, B, C, D plus T of E, F, G, H. Let's just take that guy. And what we can now do is work these out separately and add them together. So T of A, B, C, D is just, of course, A minus B minus 3C, comma, 2B plus D. And we're going to add that to the second vector here, which is going to be E minus F minus 3G, comma, 2F plus H. Everybody good with that? Did everybody see what I did? Basically, the A, B, C, and D, I'm changing them to E, F, G, and H on the second vector. Now, when you add those together, see, now you just add, notice there's no T's anymore. Once you've transformed the vectors, the T's are completely gone. Now we just add them slot by slot. So on the first slot, I have A minus B minus 3C plus E minus F minus 3G, right? All of that. Can you guys see that okay? I'm writing it kind of small here. The second entry is 2B plus D plus 2F plus H. You're just literally adding all that stuff to all that stuff. Slot by slot addition. And now you can look at that and look at what we had before and ask yourself if they are anywhere close to each other. They actually are. They're just, actually these are equal right here. They're just written in a different order, right? They're just written in a different order. The A and the E are together here, so I would need to go back and put the A plus E together. And then these two are also equal. So you could actually pretty much just leave it at that. Okay. The trick, though, let's say you were just trying to take this bottom expression and figure out what to do with it. What you want to do with it is just get all of the A, B, and C stuff and D stuff, all of the A, B, C, and D stuff together, and all of the E, F, G, and H stuff together. It's kind of a dull, boring thing to do. It's just kind of chugging through the calculation to come up with what you're looking for. Make sense? Okay, so that's how you show that T is linear. And you may want to go back and review a couple of examples of that because we haven't done it for a while. If that's a little rusty for you, go ahead and do that. Let me just ask a couple of quick final things here. And then more or less I'm going to be ready to pretty much call it a night after this one. Because the only other ones on the sheet are a couple of inner product things that you guys can check on your own. But in terms of is T one-to-one onto both or neither, that one we should be able to get pretty quickly. So is T one-to-one onto both or neither? I like these questions. There was one on the midterm, right? What would you be able to tell me about that question immediately without any more work?
It's not one-to-one.
It's not one-to-one, right? Because V is bigger than W. If V is bigger than W, then it can't be one-to-one. And so of course, it's not both. So really the only question is whether or not it is onto. Now, to answer that question, I have a couple of choices. I could work with the range. Remember that onto means that the range of T is equal to W, in this case all of R2. Or the other thing I actually could do, even though I know already that the function is not one-to-one, I could still figure out the kernel. And then the dimension of the kernel, here's the key thing, guys, and you guys, I think most of you know this because we've studied it recently. The dimension of the kernel plus the dimension of the range has to add up to what again? The dimension of V, exactly. And in this example, what is the dimension of V here? 4, exactly. So it's 4-dimensional. So I actually, the point here is, guys, is that we don't really need to do both the range and the kernel, because once we've kind of done one of them, we're going to be able to figure out the other part. So which one do you want me to practice on with you here? The range? Okay, let's do the range. Okay, let's figure out the range. So the range of t, remember the formula for it? Span of the set of transformed basis vectors, right? So I have to transform, so I need a basis for M2 of R. Well, I'm going to use the standard basis, so t of 1, 0, 0, 0, t of 0, 1, 0, 0, t of 0, 0, 1, 0, and t of 0, 0, 0, 1, right? I'm going to make that list of vectors. Okay. And I just have to evaluate each one of these things now. And you guys need to practice this again on other examples like polynomials, right? This problem does not have any polynomials in it, but sometimes people have trouble evaluating transformations of polynomials. But this one is just matrices, so I'm putting a 1 in for A, and I'm going to get the span of 1 and 0, right? And then what's t of the second vector going to be? Negative 1 and 2. And what's t of the third vector going to be? Negative 3 and 0. And what's t of the fourth vector going to be? 0, 1, right? Okay. Based on that, okay, is the range of t 4-dimensional?
No.
Please don't say that. Because look, first of all, the range of t can't be more than W, right? Even though there's 4 things here, remember that they might be LD. Now, the one that was on the midterm last week, I actually had 3 vectors and they were all LI. It depends on the problem, right? You really have to think about this. But you know that it can't be more than 2-dimensional for the range. And in fact, if you just look at it, okay, this one, you don't even need to really work at it. If you can't tell where the linear dependencies might be, of course, the way you work it out is by putting the vectors into the columns of a matrix. The pivoted columns correspond to the ones you want to keep for your basis. Now, as it turns out, you don't have to keep those two. 1, 0, and 0, 1 is an obvious choice. But you could certainly put a basis of 1, 0, and negative 1, 2 based on this calculation here, right? The first vector is pivoted, the second one is pivoted, so we would be actually throwing away the third and fourth ones in this example. Okay. Based on this, is t onto?
Yes.
If you're not sure, ask yourself, what's the dimension of the range? 2, and look at W. It is 2-dimensional, so they're the same. So the range does equal R2, so the answer here is it is onto. Okay? And we actually, because the dimension of the range is 2, we also know the dimension of the kernel, don't we? It would also be 2. Could we get a basis for it? So we got a basis for the range. Let's just wrap things up here, figure out a basis for the kernel. How do we find the kernel? Because I didn't put that on the midterm. Yeah, okay, there's only a null space if it's a transformation from Rn to Rm. Then there's a matrix, and you can talk about the kernel as being the null space and the range as being the column space. But any other example, I don't want to get... There will be a null space of a matrix coming up here, but I would rather think of this in terms of the definition of the kernel. The kernel is those vectors that get killed by t. So the best way to find the kernel is for the kernel then, is to set this answer equal to 0. So for the kernel of t, if we wanted to find the kernel of t, we would just set the result equal to 0. And yes, that does give rise to a system of equations here. That does give us a system of equations, and we can now solve it by back substitution. So there's a matrix, which would be 1, -1, -3, 0, and 0, and 0 and 2, and 0 and 1, and 0. This would be the corresponding matrix that goes with this problem. So again, you're doing a chapter 2 solution in the process of solving a chapter 5 problem. So it ties back to earlier stuff. Okay, and then this one, you could just set up free variables for it. So which variables would be free here? Let's just finish this off. I want to make sure everybody can get this right. What are my free variables in this augmented matrix? C and D, right? Okay, exactly. So C and D are the free ones. So what variables do you want to call them?
T and R.
T and R, those are my favorites. I don't like to use S because it looks like a 5 to me most of the time. I use C and R, or R and T, I mean. And then B, what would B be equal to? Say again?
-1/2.
-1/2 t, right? -1/2 t, very good. Okay, and then what would A have to be equal to? It would be B plus 3C. So it would be -1/2 t plus 3R. Okay, so to get a basis for the kernel, you guys with me? Okay. To get a basis for the kernel of t now, what do we do to get a basis for this thing? Bust out the variables. Okay, so I'm going to write something down here. If I bust out the variables, if I bust out the t's, don't write this down yet. I just want you to watch me do this. I'm going to bust out the t, and I'm going to get that. And when I bust out the r, I'm going to get that. It's two-dimensional. It's what we expected. Anything wrong with that?
It's not A or W. It's not M, Q, or Y.
Exactly. The V vector space, the kernel is supposed to be a subspace of V. So if you've written them like they look like vectors in R4, then that's the wrong thing. They should look like 2 by 2 matrices. So what you need to do is just fix this so that they look like 2 by 2 matrices. So in other words, the -1/2, -1/2, 0, and 1 would look like a 2 by 2 matrix. A, B, C, and D. Right? And then the second matrix would just be 3, 0, 1, 0. And that would be your basis. Okay? And so there's your basis for the kernel of T. So they're each two-dimensional. Make sense? Well, I've been on my feet for a long time. Let me just tell you where I got to on this sheet, because I think I am going to call it a night, because I think we're all getting a little tired. I did problem 1, 2, 3, 5, and 8, 9, 10, and 11. So the only ones I didn't do on this sheet are number 4, and 6, and 7. Number 4 is an easy one. It's actually it's just another one of these show that something is a subspace and find a basis in dimension, and it's already given in the form where you can just straight away bust out the variables. Not hard. It's easier than the one we had done earlier. And 6 and 7 are both about inner product spaces on polynomials. One of them, I gave you a proposed inner product that turns out not to work, and you just need to show me why one of the axioms doesn't work. And the other one, it does work, and they just want you to show that it works, and then again find the angle between a couple of vectors. We kind of did examples like it already. And then there's even a little bit of a Graham-Schmidt follow-up on that one. But I think you guys can probably just look at those 3 problems on the review session solutions if you need to. Does that sound reasonable? Just because my feet are killing me. Been on my feet a long time. And you guys are probably tired too. It's pretty late. So, everybody reasonably happy with this? I mean, obviously I didn't cover everything. I couldn't go over everything. But between what you already should have pretty fresh from the third midterm and what we did here, I think I gave you a lot of ideas anyway of what to go over. But don't assume that because I didn't talk about Newton's law of cooling that I'm not going to ask you about it. Okay, I just don't want you to make that mistake. There's just too much to cover in one review session. But I appreciate you guys all coming. We had a good crowd tonight, and I think we got a lot accomplished. I'll be around tomorrow if you have questions on the homework as you're trying to get that last 2 problems done for the semester. And then I'll be around all weekend with more office hours, and I'll be reviewing again on Sunday evening for the review session. So, all right, with that, I'm going to let the camera be turned off. Thank you.